Good afternoon, everyone. So we are waiting for the screen to show up. In the meanwhile, let me just try to give a response to a number of questions you asked either yesterday or in the morning. So the first question asked yesterday was as follows. I talked about deseparation. And then what if you have hidden variables right there, right? You have graph, you want to apply deseparation to see whether variables are independent given something else. What if you have hidden variables? Do you remember this question? Okay, so basically I gave a very short response. However, it's better to spend a bit more time. Remember, we are talking about a graphical model, it's given. And if you have hidden variables, in principle, you should try to include that hidden variable in the graphical model. In practice, it's hidden because you cannot measure or control it, right? However, in the graphical representation, clearly you should have it. Still waiting for, there's some problem right here. Let me just, close all other windows. So let me give an example. Suppose here we have X, Y, Z. And here we have something, but this guy is not given. Then in the graphical model, we still have this one because we use the graphical model to really represent the underlying process, underlying property, right? Without really having a model of the underlying process, we cannot move forward. The problem is, since this guy is hidden, we can never control on it. We can never kind of condition on this guy. As a consequence, you will always observe that X and Y are dependent, given anything you have, right? So this is a good. So in the graphical representation, you can easily incorporate hidden variables. You don't care. However, in practice, you cannot measure the values and you cannot control for that variable, and you cannot condition on that guy.
Given anything observed, right?
Yeah, given anything observed. You mean? Oh, yeah, you're totally right. Given anything you can observe, the two variables will be conditionally dependent all the time. Yes. And the second question was about equilibrium state data. So very oftentimes we have data collected in the equilibrium state. No, it's good. It's good. I just didn't get time to do it. So try to answer the following question. Usually it takes time for causal inference to take place, right? So if you really have the data generated by the causal process measured at the right causal frequency, then everything's so simple because you have time order as an indicator of the causal direction of causal influence, right? And you have the right, you just do regression if there are no compounder. If there are no latent compounder, you can even do Granic causality to find the true causality. But now we are talking about problems that seem to be harder. Why? What kind of data do we have? No, there's another problem. So whenever I use full screen, it says you are using another screen. See, if I play. See, it's paused because it's a different. Yes. Okay. Maybe you can help.
Yeah.
Sort it out.
Yeah.
Okay. So, what kind of data do we have in causal discovery? So far, we haven't really talked about how to make use of temporal or time information in causal discovery, right? What kind of data do we have? What kind of data can we analyze? And furthermore, we have a causal discovery method. We can apply the method to a lot of data. Are we sure that the final result produced by the causal discovery method, like PC, is really consistent with the underlying true causal process? Right? You don't really have the data directly generated by the causal process with time information. How can we interpret such results? Specifically, In some cases, we may just have data collected in the equilibrium state. For instance, let's talk about demand and price. Demand will influence price, and price will influence demand, right? And then in each of those areas, in Texas, California, Pennsylvania, and so on, you can see if you have a new product, after some time, the process involving the two processes, including demand and price, will converge in some way. Essentially, you are going to have the equilibrium state of the process. In each state, you can just have a one value after you reach the equilibrium state. Is that right? And then you may want to analyze the data with causal discovery methods, like PC. How can you interpret such results? And in some cases, we don't have equilibrium state data. Instead, we may have aggregated data. Consider stock returns, daily returns. So we care about some companies, and we try to see the causal relations among a lot of companies. We know that in the stock market, if one company influences another, then the causal influence is very quick, right? Within 1 minute, the influence will be done. However, very often we just use daily returns. Essentially, daily return is nothing but the aggregation of the short-term returns within the day, right? Then we may discover some results with, say, those methods you are going to see tomorrow and the day after tomorrow. How can we interpret the results? Do you think that's really causal? Do you have such concerns? Right? Without answering those questions, how can we really apply method to any kind of data? Okay, so basically, here's the message. By the way, would you like to share anything? If you work with real data, clearly this is the concern. Would you like to share any kind of opinion or concern or any findings? Anyone? Okay, let me share something. So first of all, later you can see that if you have the equilibrium state data, the discovered causal model from such data is consistent with the underlying true causal relations in the true causal process, qualitatively speaking. You can show that. However, of course, since you don't have time information, you may not, in some cases, with particular methods, you may not be able to discover the causal influence or causal direction for each causal link. That's the problem. But basically, if you can discover something, you are sure it's there. Although you may not be able to really estimate the quantitative causal influence. Okay, later you see why. And furthermore, if in the true causal process, there are no cycle, say X causes Y, without Y causing X, then in the discovered causal model, you will see the same thing. X causes Y without time information, right? Or instantaneously, X causes Y. That's it. You can see it. And similarly, if you work with aggregated data, the situation is slightly more complex. But in the linear case, that is the causal relations you can discover from aggregated data are also consistent with the true causal relations. If you don't really care very much about the quantitative causal influence, qualitatively speaking, they are consistent. However, in the aggregated case, if the relations are nonlinear, sometimes the discovered results from aggregated data could be very noisy. They could be very different from the underlying true causal relations. So we have some ongoing work on that. Okay, to summarize, if you really have the data generated by the original causal process with time information, everything is simple, right? Of course, sometimes in some situations, you may want to deal with the latent processes. It's possible, but basically you have time information. And in practice, very often in biology, finance, and so on, you may just work with the data collected in the equilibrium state or data that are basically aggregated data. Generally speaking, don't worry, because you can still discover the true causal relations or true causal structure. But in some cases, you cannot recover all the causal parameters, coefficients, because you don't have the information of self loop. If X influences itself, right, after some time delay, given the original time series, you can recover the self loop information. But if you have the data collected in the equilibrium state, or aggregated data, you don't have such information. You cannot estimate self-loop. And as a consequence, the estimate parameters might be different across the two scenarios. In one scenario, you have two data generated by the temporal causal process, and in the other, you only have kind of very bad quality data. But you can see the difference, right? And you can see how they are consistent and how they are different. I think there was one more question. I just try to make those things more detailed so that we have everyone is on the same page. Did you? I think there was one more question, right? The last one, is that right? Did you ask two questions? Yes, you also, yes. What's that question?
Oh, you mean today?
Yeah.
So can we use the Bayesian rule?
Oh, yes. Okay, good. By the way, Peter gave a wonderful response. I just try to make things more more detailed. Basically, you first gave another one, sorry, name. So you asked whether we can, very often times we do regression and we see in which direction is more significant. And here you didn't make it very specific what you mean by significant. You may say coefficients are significant. Or you may say, oh, they are significantly independent, or right? So it really depends. So if you talk about significance of the parameters, basically, very often you can show that regression is qualitatively symmetric. If the regression coefficient from A to B is significant, then generally speaking, the coefficient from B to A is also significant. However, you can really see the asymmetry if you rely on, say, independence of the residual, given a constrained functional model, right? So I guess probably that's something you have in mind. You're talking about significance of some other thing, say independent test.
I think I was talking about the significance of the coefficient, the p-value.
Then basically regression, although regression is not symmetric, you can see different parameters, but qualitatively speaking, it's significant. Why? Because as long as two variables are conditionally independent, given the remaining covariates, then the coefficient should be non-zero, no matter in which direction you are doing regression. That's why, qualitatively speaking, we cannot discover any causal information by making use of the significance of the parameters. But we can go further by making use of additional information. And then, of course, now you can see you want to make use of the asymmetry. And you can use the frequency framework, or you can use the Bayesian framework. It doesn't matter. Later, you see how you can really formulate the asymmetry of the causal direction, or asymmetry of the two variables, even without the time information. Okay, cool. Today, in the afternoon, let's see how we can identify causal effects, and then based on that, how to do counterfactual inference. By the way, for this part, I guess most of you are really familiar with the identification of causal effects, so it's going to be very quick. And here we have multiple experts in the room. Please just jump in whenever you would like to share anything. So we'll see the problem definition, and then we'll briefly talk about potential outcome framework. And you'll see why propensity score is useful in principle. And then I will just give the graphical criteria for identifiability of the causal effects. And then you see how we can do counterfactual inference in a principled way. Remember the three types of questions: prediction, intervention effect, and counterfactual questions, right? Good. Now we try to answer the second one. Basically, we try to see the probability of the target variable given intervention on some specific variable on the population level, right? For now, we don't have the evidence so that we can say something very specific about the particular subject.
Can I ask questions about population in counterfactual? For counterfactual, you have a question for an individual, right?
Yeah.
Can you ask question about a population?
Okay. So here by population, do you mean the original population or some subpopulation?
Either.
So if basically this, as you can see from the formulation of the questions right here, in counterfactual reasoning, we are trying to talk about the specific subject by making use of the evidence. Once you have evidence, you are not talking about the original population anymore. However, in many cases, you may not be able to really say very much about this particular unit, particular subject. As a consequence, in some situations, you are considering a subpopulation or subgroup, and you want to make it informative relative to this group.
Thank you.
Okay, so you saw this picture before. A kind of golden standard way to identify causal effects is to do this kind of randomized controlled experiments. It's hard because you have to make sure the two groups really have the same, either same values or same distribution for the remaining features, right? That can influence recovery, the target variable. It's really hard. Then we want to make it simple. As you can see from here, intuitively, it's very simple because this is the conditional distribution, which is purely statistical, and this is a causal effect. Formulating this equation is not so easy. But once you have this equation, everything is so simple. You just want to see the effect of intervention on treatment T on recovery, right? That's it. So you just do intervention. You can imagine that you can do intervention. And after you do intervention, they will become independent. Then you have this equation. This is nothing but a surrogate way to do randomized controlled experiments. Because if you really do randomized controlled experiments, they will be independent. Other kind of related factors will be independent from treatment. Now you can imagine the other way for you to do randomized controlled experiments, and then you can try to infer those things by making use of observational data. And that's also why it's called observational studies of causal effects, right? So the setting is very clear. You cut it off, and then you can see why you go from prediction to identification of causal effects. Exactly the same thing. The only difference is that you don't really have to do either intervention or randomized controlled experiments. Okay, first of all, let's have a look of the very kind of basic definition of identifiability of parameters in statistical models. So everyone in statistics, right, is familiar with the definition. Basically, we only say parameters are identifiable. We mean the following thing: different parameters will correspond to different distributions. Or in other words, if two distributions actually are identical, then the underlying parameters must be identical. This is good. That's why identifiability is so important in causality, not just in causal inference, identification of causal effects, but also in causal discovery. Right here, you want to identify causal effect of X and Y. Clearly, you want to make sure that what you can estimate from data is the same as the truth. Suppose the truth is here, theta. Now, given the something you can observe, you want to make sure that as long as I can really generate the same thing you can observe, then the underlying parameters should be the same, meaning that I can recover the truth. The same thing happens in causal discovery. I have a structure right there. It's hidden, but the structure generates data. Now, I use another model to explain exactly the same distribution, right? And then I have to show that, oh, this structure I'm using to explain the data must be the same as the underlying truth, at least up to some equivalence class, right? So that's why identifiability is so important. And that's another way to distinguish between causality research and traditional machine learning. Okay, then we have the definition of identifiability of causal effects. It's just followed from the previous definition. Here, the only thing that we are concerned with this causal effect. This is one way to denote a causal effect. It's a distribution of the target variable Y given the intervention on X. Because here we try to see the causal effect of X on Y, right? We want to see this guy, and Pro uses this notation. So basically the same thing. Okay, just different notations. Okay, so you want to see whether this one is identifiable, given observational data, and one more thing, which is the causal structure. So you have two inputs. One is the qualitative structure. The other is the observational data for the variables that you can measure. Okay, then the definition as follows. You have two models. The two models share exactly the same structure, which is given, and the same observational data, which you can measure, the observed data of the variables you can measure. And then you want to see whether they always give exactly the same causal effect. If they always give the same causal effect given by this notation, then you say In this case, the causal effect is identifiable, right? It's the same thing. You just replace theta parameter in the previous slide with this quantity. Good. Now let's look at this example, or I can give you more examples. So right here, this is a scatter plot of X size and cholesterol. Right here, you can see different age groups. Right here, age actually is the cause of both X size and cholesterol. Suppose that's the case. And then you can see the dependence. And of course, this is another example to illustrate Simpson's paradox. Because if you ignore age information, the correlation is positive. But if you know the age information and fix it, then clearly the relationship between X size and cholesterol is negative. The more X size you do, the less cholesterol you are going to have on average, right? That's good. Now let's suppose we only observe the data for X size and cholesterol, meaning that age here is hidden. We know this is the true causal structure, but we cannot measure the data for age. In that case, we have the two things that will be shared by different models would be this structure and the data for X size and cholesterol. Now let's try to see whether this link or property of this link is always the same across all possible models. If this guy must be the same, then we say the causal effect of X size on cholesterol is identifiable. Otherwise, it's not, right? Now intuitively, you can see, we see the correlation between them, right? From observational data, we can see the correlation between X size and cholesterol. That's it. And then clearly you can see different models in the linear case with different parameters that can satisfy the structure and the distribution for X size and cholesterol, right? But the models are different, the parameters are different. So clearly, if you only observe this guy and that guy, the causal effect of X size on cholesterol is not identifiable given this structure, right? Of course, you know why, because here we have a latent confounder, right? Later you can see, or if you know this guy, clearly it's identifiable. Yeah.
So that the older people will access more, because in the data, it's higher. When it is higher, the X size is higher. Is that what that means?
Pardon me, this is just an artificial example. So I agree with you. So ignore that part. You are totally right. That's questionable. Okay, is that answer to your question? Yeah, generally, I mean, that may not be true. However, you can also think of the example involving kidney stone patients, right? That one is a real data set. So good.
Can we summarize kind of why it's on right? So now we have this age, right? We don't observe it.
Yeah.
So it's not identifiable because we can include age and have different structure.
Oh, age is there.
First, the age sign.
No, the structure is always given. The structure is always given in identification of causal effects. However, with the same structure, and furthermore, the same distribution for the measured variables, X size and cholesterol, you can have different models in the linear case, right? It's given by coefficients right here. So you can have different models to satisfy both of them. The same structure, the same distribution for the measured data. You measure variables.
Structure, the first structure, if there is no way.
Oh, by structure, yeah. By structure, I mean the qualitative structure without coefficients.
Okay, so the first structure is we have X size and cholesterol, so there is one age between them, right? So we want to see whether this age is identifiable or not, right? That's a problem we are trying to.
No. Now we are not trying to discover any kind of structure information. No, the structure is given right here. Age is a common cause. As you can see from here, the two models share the same structure, right? Because the qualitative structure is the same. Age causes X size causes cholesterol, age causes cholesterol. It's the same thing shared by the two models.
Yeah.
And the two models are different because I use the thickness of the, right here, the thickness of the edge to denote how big the causal effect of the parameter is. So you can see there, the parameters can be very different.
So the thickness is a parameter, so.
Yeah.
Okay, now it's clear.
Okay, good, good. Any other questions? So they have different parameters, but you can have the same distribution for the two measured variables. That's why the causal model or the causal effect of collateral on xi, of xi on collateral is not identifiable. Good. Now, potential outcome. So basically, in this case, you can see, suppose we are doing a treatment. And then if you do, well, first of all, let's see the notation. For particular subject or unit, the I is 1. You can do intervention. On treatment, you can set the treatment to 1 or 0. And then you have this note, right here, you have this notation. This is the Y value for the I subject given the intervention to set T to 1, right? And this is nothing but a kind of a short, very, very good way to put it, right? YI 1, just a shorthand. And then we say this is the potential outcome. Later you can see why, because in practice, right, by the way, here you can see the notation. T is the observed treatment, Y is the observed outcome, and I is the index of the subject. And then we say this is the potential outcome because in practice, for the same subject, you can only do at most one of them, right? You can set T to 1 or to T to 0. And then the other is hidden. You cannot observe it. So that's why it's potential, clearly it's a potential, right? Because you cannot really observe them at the same time. And in practice, you may have one, you may observe one of them, as you can see from here, then the other must be unobserved, which is counterfactual, right? Because you cannot really see it in this actual world. And the causal effect right here, very simple way to put it is to use the difference. So for the I subject, I would like to see the difference in the value of Y because of the different values of the treatment, right? So this is one way to see how, say, vaccination is effective relative to the I subject. Okay. So then you can see basically this is a missing value problem because for this one, I have value for 0 for the first subject. I have a value if the treatment is 0, but I don't have the value for Y if the treatment is 1, right? So we have a lot of missing values. The problem is, given so many missing values, how we can estimate this causal effect, right? We have to make assumptions. Now let's see how you can proceed. Right here, this is just a summary, and we want to go further. You want to find this guy. This is a expectation with respect to different subjects. So you want to see the average causal effect. Okay. So right here, you can see the assumptions, traditional assumptions you can make in order to estimate the causal effect. So the most kind of traditional one is ignorability condition. And you can make it more practical by considering some other latent, common causes, and then you have conditional ignorability, basically, and then you have positivity of the conditional distribution. You have to assume that the outcome for a particular subject depends on only the treatment on this subject, but not the treatment on any other subject. So basically, this is no interference assumption. And then you have the assumption called consistency. Usually, this one is pretty trivial. It says that if you really have the treatment, so if you really have the treatment, then the actually observed outcome should be the same as the potential outcome. Okay, later you can see the formulation. Good. Now let's have a look at the ignorability. Basically, here we have independence between the variable of treatment and the outcome, the potential outcomes. Good. First of all, let's see how we can understand this thing. The potential outcome, this guy actually can be considered as a variable because this one includes the generating process of the outcome given the specific treatment for the subject, right? So this is just a mechanism. This includes all the information you need in the generating process of treatment of outcome given the input. And then in this case, right here, you can see this one represents the property of this link from treatment to the outcome, right? And intuitively, this property is clearly irrelevant to how you select the value of t, right? There's no way for them to be related in the graphical representation. So essentially, we say this variable, although this variable is dependent on y, clearly they are dependent, but this variable will be independent from the mechanism here. Again, this is the modularity condition. So let me write down. You have dependence between t and y right here. However, if you fix the value of t right here, as you can see from here, now with this notation, we are talking about the property of the generating process from t to y, right? Because you fix the value of the input, then this is nothing but the mechanism right here to generate the outcome from the input. Remember modularity property. Here, there's no other way for them to be related. As a consequence, this variable will be independent for the other one from y if you fix t value. So here, if there are no confounder or common cause for treatment and y outcome, then this condition holds true. Okay, this is ignorability. And you can see the graphical interpretation of ignorability. It's just a specific type of independence between random variables. And one random variable, as you can see from here, is nothing but a way to represent the mechanism to generate the outcome from the fixed treatment. Okay, good. This might not be the optimal way. I mean, some of you may have a better way to put it, right? If you have better way, please just let us know. And then, given that, we can do the following thing. Suppose we want to find the average treatment effect. We want to find the expectation right here, because we want to get rid of the index of the subject. And then this is trivial. We just have expectation of this guy given T1 minus this guy expectation given T0. Why? Because T and Y are independent. So you can condition on that guy. And then this is nothing but the estimated expected outcome given that T0, right? Now you have two groups. In one group, T0, say control group. In the other group, T1, say treatment group. Then you can just calculate expectation and then take the difference, right? So if ignorability holds true, you can just find the average causal effect this way. Good. And so now let's have a closer look at the assumptions. So first assumption is ignorability. So basically it's about the independence. As you can see from here, in this example, you just take the average here, and you take the average here, and then you can take the difference. And this is the average causal effect. It's very simple. Now let's consider more general situation or more difficult situation. Right here, this is age. Remember previously we have age, exercise, cholesterol. Now clearly, the generating process of y given t, and the generating process of t right here are dependent, because x value will influence both of them. Will influence what value t takes, and also will influence the causal mechanism, right? For you to generate y from t. Good. In this case, clearly they are usually dependent. We don't have this condition. And then how can we move forward? Now you can see the following thing. Given x is the only way for them to be related. X is the only way for the random variable t and the treatment effect mechanism from t to y to be related. Then if you condition on x, the two things will be independent, right? So now we just further condition on t, condition on x, because x is the only way for them to be related. And this is nothing but a conditional ignorability, because if you condition on this guy, then you can ignore treatment when you try to say something about the outcome given treatment. And then if you have this one, first of all, you can estimate the so-called conditional average causal effect right here. You condition on a particular value of x. You are given particular value of the feature x, and then you can see, oh, I want to, given this one, I want to see the expectation right here, because I still have the some other kind of random effects. And then this one is trivial. And right here, again, we can introduce t in a condition set, because given x, t is independent from the potential outcome. And then we have this equation, and then this is nothing but the difference in the expectation y across the two groups, giving the same x value, right? So this is the conditional average treatment effect. Good. And then we can go from conditional average treatment effect to average treatment effect by further conditioning on x, the features. Right here, we take another expectation, and then we have that. Okay, that's very simple. And we need some additional assumptions. First of all, we need a positivity assumption. Basically, it says that given the value, each value of the feature x right there, the probability for treatment to be 1 or 0, right, is between 0 and 1. There's the chance for this guy with x value to receive treatment or to be in the control group, right? So basically, this is a positivity assumption. The probability distribution, condition probability right here, should be positive. And then under that condition, we can just go further. I'll skip those things because I think here I'm giving too much detail. Given that you are a lot of you are from statistics, you are super familiar with everything here. Is that right? In case this part is not very familiar to you, please let me know. Oh, we have, okay. I will slow down a little. So the third assumption is no interference. Generally speaking, or intuitively, this assumption is kind of trivial in most cases, because when you try to intervene on this guy and see the effect, generally speaking, you don't care about the treatment on other subjects, right? Suppose you want to see the effect of vaccination on me, then generally speaking, you don't care about the effect on other people, right? So mathematically, it's the following thing. This is a potential outcome for the I subject, given the treatments on a lot of subjects right here. And then this one is nothing but the potential outcome for this object given its own treatment. You can ignore all the remaining treatments on other subjects, right? So you can just ignore those people. That's why we say there are no interference among those subjects. Okay. And then we can make things so simple right here, as you can see from here. So you can see the illustration. We do intervention, then we just care about only this particular treatment. I can ignore all the remaining subjects in this case. The last assumption is about consistency. Essentially, it reads this way: the potential outcome under treatment t, which is y of t, is equal to the actually observed outcome if the treatment is really t, small t. So if t takes this value, if the variable treatment takes this value, 0 or 1, then the observed variable should be the potential outcome. Okay, so generally speaking, that's true. But you can find some very ugly examples. This is one example. So here, suppose we have a treatment, right? If treatment is 1, I get the dog. If treatment is 0, I don't get the dog. Okay, you have two possible values. And then, so in this case, I get a dog, I'm happy, good. But here, I get a dog. Actually, there are some other factors. The dog is white. I'm not happy. So in this case, you can see you don't use sufficient information of the treatment. As a consequence, this is violated. Even if you have this treatment, for some other reasons, actually, the actual outcome right here is different from the potential outcome. And this is a very weird example because the treatment, the description of the treatment is not complete in this case.
So the question, if the treatment has a dosage, like a dose of
Yeah.
the drug, would this be about?
Exactly. Yeah, it could be the case. Exactly. Okay. Any other questions?
In that case, I would make the treatment, the dosage is part of your treatment.
Yeah, that's a very good way. Yeah. So you want to make the treatment more complete so that this is true. Okay. And then now you can see the summary of the conditions. Ignorability or conditional ignorability are really fundamental. Later, I will give a graphical kind of counterpart, graphical criterion as a counterpart of this condition in the different framework. And then we have positivity. With this one, we can really do the calculations. And we assume there are no interference, we assume consistency, and then we can just go further to estimate the causal effect, as you can see from here. Average causal effect, basically here, we can just write, I really should use my iPad. Let's try. So, good, it works. So right here, first of all, we have no interference. That's why we can just use the potential outcome, right? And then this is just a linearity of expectation because expectation is a linear operation, and then a linear operator. And then we can just go further by making use of the expectation. And we go further by making use of, by further incorporate T treatment right here. Then we can consider the two groups. In the first group, T is 1, and in the second group, T is 0. By the way, we are doing this because, first of all, if you really have randomized controlled experiments, what will happen? Then we don't have to go so far, right? Because in that case, clearly this condition ignorability will hold true, and you can just do the comparison. You can just compare the average across the two groups, right? That's the first part. If ignorability holds true, we don't have to condition X. Now we condition X first, and then we remove X by further condition X. Okay. However, when you condition X right here, you are supposed to use the same distribution of X, right? Otherwise, probably you are using the conditional distribution of X given the group, given T. That's the kind of mathematical way to find the conditional distribution. But now we have to use the same distribution of X across the two groups. This is in this group T is 1, and in this group T is 0. Suppose this is control group and this is treatment group. Now the only thing is that we have to use the same distribution for X when you calculate this conditional this expectation, right? And that's the issue we are going to solve right now. Apart from that, everything is very natural at this moment. Good. Oh, it's coming back. Okay, so how can we, now we have, it's good, we can wait. We have a control group where T is 0, and we have a treatment group where T is 1. In the two groups, the distribution of X can be very different. And that's why X and T are dependent in the general case, right? X and T are dependent. Otherwise, you have randomized controlled experiments. What can we do? How can we really make use of the same distribution of X when we calculate the two quantities, as you can see from here? How? Any idea? I mean, people in machine learning, right, and statistics would automatically come up with a lot of solutions. And then you can just compare your solution with the classical ones. You'll see classical ones in a minute. You just want to make sure you use the same distribution of the feature X to calculate this expectation across the two groups. I'll skip this part. This is very general. Basically, in statistics, you care about the estimate, and estimation. Estimation the procedure for you to find the estimator. Here we say this is the causal estimate because this is you can see the causal notion, and then here you can see the statistical estimate because right here we can just find the expectation. It's purely statistical. So here we want to go from the causal world. Specifically, we want to say something about causal estimate, like causal effect. And then because of identification or because of identifiability of the causal effect, we can just use some statistical notions to solve the problem. We use statistical estimate. And then the procedure to find the value right here is the estimation. And here you can see the example before I really talk about how to deal with that problem. Right here, this is the simulated data. We know the true treatment effect is 1.05 right here. We have two models, we have outcome, we have treatment, we have covariance right here. And then you can just apply the procedure. And here, I use a linear regression. Later, you can see what I mean by linear regression. And then I can solve the problem. Okay, now you can see if you use the treatment effect, the estimate right here, this is the estimate error because we have the true value here. This is simulated data. That's why we have the truth, right? So with this method, the error is 19%. But if you just use the statistical estimation procedure by using the conditional distribution, traditional conditional distribution, the error is large, it's huge, right? So that means clearly you have to use the causal method if you want to see causal effects. Okay. So in this case, as I just mentioned, if you count randomization, then they are independent. Everything's so simple. Otherwise, you have to make sure you have the same distribution for X across the two groups. And here you can see what method we can use. First of all, we can use the so-called regression adjustment, and you'll see how to do so in a minute. And alternatively, you can use matching. You can try to use some techniques involving matching to make sure that the two groups will make use of the same distribution of the feature X. And there are some other methods, including inverse propensity score-based method and a doubly robust method. I will skip those things because they are kind of slightly more complex. But if you're interested, you can talk to us afterwards, or you can just read something. When are we supposed to take a break? 2:20 then. Oh, maybe then we can wait 2 minutes. That's good. So now let's see why regression adjustment is useful and how to do it. Basically, the problem is as follows. You want to find this average causal effect right here. You see this equation, right? Previously. Now, if you have a conditional model for y given x in each group, denoted by mu, then you can solve the problem. Because if I have the conditional model, I can just use the same distribution for x to generate the value of y across the two groups. I have two regression models, right? Two conditional models, one for the control group, the other for the treatment group. As long as I have a valid conditional model, then I can immediately solve the problem, right? Because right here, I can suppose this is a valid conditional model. The expectation of y given x in this group, this is mu0 is the conditional expectation of y given t0 right here. Then after that, I can just use the same values of x as input, right? And then I can just calculate the difference, right? Why can we do so? It's because we already have the conditional model or some kind of regression model so that we can derive the conditional mean of y given any value of x, right? Some of you look kind of puzzled. You want to answer right here, you want to answer this question, right? So if you have a right here, this is a, it's hard. Why? Because across the two groups, you don't have the same distribution of X. Because some of you look puzzled, let me wait a little bit. Is that right? Remember the example involving the symptom paradox example. Let me just write down. So you have here, you have T, you have outcome. This is the stone size. This is treatment, this is outcome. Right? Stone size, in that case, you can see the stone size and treatment are dependent right there. So that means actually you have two groups. Suppose this is the kind of control group and this is the treatment group. Right here, the distribution of X, you can discover the distribution of X in each group. What's that? It's a conditional distribution of the feature X given the treatment, right? So you can discover the distribution of X in this group by looking at all subjects in this group. Then you have kind of this distribution, empirical one. And similarly, you can have the distribution for condition on T equal to 1. But if you want to estimate this guy, you have to use the same distribution for X. Now comes the problem. I have an X here, X say X1 is here, but X1 does not appear here. Why? Because the same subjects can only receive at most one treatment, right? So I cannot use the same X value or the same X values across the two groups. But I have to make sure that the X distribution is the same when you calculate the two terms. What can I do? Right? This is the first way. Now, suppose in each group, I can find a conditional model, say linear or nonlinear regression model of Y given X in each group, right here, this group and that group. Now, since you have a model, you have a prediction model, you can just use all the X values across two groups as input. Then you have the predicted value of Y, right? And now you can just calculate the expectation and consider the difference. Because now you are using the same distribution of X. Why can you do so? Is because I can predict the value of Y given any value of X since I have the model, conditional model, mu1 and mu2. Good? Okay, so this is basically regression adjustment. I'll give example later. This is more specifically here the procedure. So sometimes you can use linear regression, and sometimes you can use non-parametric nonlinear models to estimate the mu, because it's nothing but sometimes regression model, right? And then after you do that, you can just estimate this guy by considering the difference, difference of mu for the same value of X across the two groups, right? Now you can just use whatever value you like for X. You can just use all X value here and all X value here. Clearly, you are using the same distribution for X when you calculate this guy. Okay, so now you see how we can do regression adjustment. Let's go further. Alternatively, you may want to do some kind of matching. So I have data points here, Xi here, and X here. For instance, for each value here in this group, I just want to find a very close one in this group. And if in the extreme case, suppose they are identical, for each of them, I can find a kind of identical one, and then I just use those values. I just throw away the remaining values and just use those values that are selected in this matching process. And this is another way to guarantee that I have the same distribution of X across the two groups, because I threw away other data points right here to make sure they match each other. Okay, intuitively, that's the idea. Is that good? Now you may want to see how you can really do the matching process. Intuitively, you may say, oh, here I have the value of x, right here, x1, x2, x3 is actual value. Can you see it? Might be too far. Okay, so this is the x first value, x1, second value, x2, and so on. Now, you may want to start with some kind of distance for the x values, right? So basically, you can use a regular distance matching, as you can see from here. You have this distance between two different x values. And after that, for each value of x in the treatment group, you just want to find a value in the control group with the smallest distance right here. You do the matching, and then you throw away the remaining data points in the control group. Now they are aligned, right?
So this is based on the assumption that this captures all the causal variables, right?
Oh, okay. We assume that's the case, meaning that there cannot exist, say, something here, right, at common. You're to the right. We assume that's the truth. Yeah. Otherwise, if you have such a guy, C, which is not measured, then the conditional ignorability condition will be violated. Okay, so here you can directly use distance. However, go ahead. X, S. Oh, S is basically the way the covariance matrix to normalize the, yeah, this is you can use Euclidean distance, but very often times you may want to do some kind of normalization based on the covariance matrix of the features, especially if you have high dimensional features. You may want to normalize the feature in some way by making use of this sample covariance matrix. This is a sample covariance matrix of X.
The intuition of this distance.
Oh, this is nothing but kind of normalize the Euclidean distance. Yeah.
So is that similar to the simple vector machine? See, SVM, it looks like very similar to the SVM to find the minimum distance for the simple vectors.
Yeah, I would say you're right. At the same time, this one is much simpler. You just want to, let me give an example. So you have X1 here, right? And this is the first subject in the, say, treatment group. And then you just want to find the value of X in the other group that is closest to this one with the minimum value of the distance. That's it. That's why we say it's a matching process. After that, you just keep that value. You go through all data points, you keep those values, and throw away the remaining values. Now you can see they are kind of approximately speaking, they are almost identical, right? And then we have the same distribution across the two groups. Good? Yeah.
So in reality, we did a lot of propensity matching, and then we noticed the sample size between the two groups is really unbalanced. If the sample size for the treatment is relatively small, I understand we can find the potential peers from the control group. But if it's a vice versa, is it going to produce the bias?
You're totally right. There are so many practical issues if you use those methods. Is when you use the matching methods, there are so many issues. That's a very good one. Actually, we are going to have a discussion at the very end of this part. Wonderful. Actually, now let's look at the first issue related to what you just mentioned. Very often times you have high dimensional features, and it's really hard to do matching in the high dimensional space, right? Because if the dimensionality is very high, then the data could be very sparse, right? And really the measure of the distance could be not kind of reliable. What can we do? So you can use propensity score. Basically, propensity score is also random variable. Is nothing but the conditional distribution of the for the treatment to be 1 in this group, given the value of X features. So this is just the probability given any X value right here for the feature, the age. This is nothing but the probability for this one to be in the treatment group. Okay. If you fix the value of X, this is nothing but the function of X. For instance, the function may look this is X, then this would be this is the E of X, right? And this function looks familiar. For instance, if as X increases, the probability for X for the subject with this X value, right, is more likely for the subject with the X value to be in the treatment group. Then this is how the curve, this curve of this function looks, right? If you are familiar with the classification, basically it's something like logistic regression. You want to find a conditional distribution of treatment given the features. Okay, and if you consider X right here, the original variable X, then you have this guy. E, the function of the random variable X. Now this guy is a random variable because a function of random variable is random variable, right? And this is just a propensity score. It's a random variable. However, later you can see, although this function is so much simpler than X, because this guy is now one-dimensional thing. X is high dimensional. Now this one is so simple, right? Because every time it's just a value between 0 and 1. Good. Later you can see matching the covariance X is equivalent to matching the data points based on the propensity score. You just want to use the propensity score instead of the original features in the matching process. And you'll see why. So right here, this is the definition. This is propensity score. And then given the definition, you can see T and X, treatment and X are independent given the propensity score. This is the tricky part. So right here, this is X, this is T. You can see this one, the propensity score is in between, right? Because it's a function of X to capture the information Y of T. Given X as the input, you want to use this guy to predict T. And this one contains all the information of T given X. In other words, if you know the propensity score, then you don't have to use X when you try to predict T, because this one just gives the value as the probability. That's why treatment and X covariance are independent given the propensity score. That's very nice because the treatment is independent from this high dimensional vector given this very simple function, a simple random variable. Okay, that's the propensity score. And then in the next slide, you show that we can just use E, the propensity score instead of X when we try to do the matching. Let's go there. This is the original one. So this is the expectation of Y given T and X with respect to T to X. Remember that equation? Oh, I should go back. This one is nothing but, let me write down. Expectation with respect to X, expectation Y given T, and X. Right? So here, this part, you condition X in this part, and then you find the expectation with respect to the covariance X. This is what you have right here, the second one. Okay. And then you can see that after some rather straightforward procedure, you can just replace the features of the covariance with the propensity score. That's all. It's the same thing. Given this equation, what does it mean? It means that from now on, I can forget about the original features. I just use the propensity score to do everything. Right? Okay. Now you can just use the same procedure of matching, but you just use the propensity score. This is a summary right here. So this is first of all, you may want to find the propensity score for each value of X, and then you can just do the matching across the two groups based on the propensity score values. So for each X here in the treatment group, you want to find the propensity score, and then you want to find the data point or the subjects in the control group with the same or almost identical value of the propensity score is done. Okay, so that's the matching process. So right here, first of all, do you think it's a good thing to use the propensity score instead of the original features? Generally speaking, it's good because now you don't have to use the high dimensional features, right? I think in statistics, there have been quite some arguments regarding whether it's really good to use the propensity score, but in theory, you can see it's so much better. And right here, the second condition is to assume that the density, the distribution is positive. Here, if you use the propensity score, can you avoid this assumption? Propensity score is just the probability of T. We assume previously, we assume this guy. This one is the positivity assumption, right? And actually now you can see this is nothing but the propensity score, right? So can we clearly, you have to follow this assumption because if this one is 0 or 1, then we cannot do the matching because all those data points basically will have the same value and then it makes no sense to do the matching. Essentially, that's why we still need to assume positivity. Propensity score is just a way to simplify the matching process and make calculations simpler. The underlying assumptions are exactly the same thing. Okay, so this part is very quick and could be messy because I don't really want to talk about this part in front of certificates. But is there any question? Yeah. Yes. One to many, you mean here? Oh, yes, that's a very good point. Can you? Generally speaking, you cannot, because that way the distribution across the groups is not necessarily the same. So generally speaking, you should try to avoid that. Otherwise, for instance, you may have a lot of data points here mapped to a single value here. Clearly, the distribution is different. So yeah. Good. Yeah, please.
I'm trying to find the propensity score to a real case. For example, we have some patients, and we test 3 genes for each of the patients, and for each of these they have 0 or 1. So there will be 8 cases in total for 8 possible cases of the
for which variable?
For one patient, they will have for the patients, the 3 genes combination will have 8, right? 8 cases.
Yeah.
And then if we use the propensity score, we can give them from 1 to 8 to denote these 8 cases. And if the score matches, and I can match the 2 patients to the same group.
Oh, very good. But basically the question is, what if T has multiple possible values? Is that right? So right here, T is binary. It's control treatment.
I mean X.
Oh, X, then it doesn't matter. So it doesn't matter because here we assume X could be continuous.
Okay.
So as long as you have that function, the propensity score function, then you don't care, just follow the procedure. Even if X is high dimensional and continuous, it doesn't matter. Yeah. Okay. Yes, that's a very good one. So I think maybe I should invite a statistician to answer this question because I didn't really play with it, although I know some theory. Would you like to give a response? Oh, okay. Okay. Anyone? Oh, then I should have spent more time on it. I thought everyone was familiar with it. That's why I was kind of eager to finish this part. Okay, now let's discuss it. What if T has multiple values, right? More than 2 values. Okay, any idea? Sorry? Empirical
distribution for entities similar like to using the chi-square test or something to make the similarity, to measure the similarity.
To measure similarity. Oh, first of all, let's try to answer the question step by step. First of all, how can you define propensity score? Originally, propensity score is like a binary classification problem, right? I just want to see the probability for X to be, given this X, I want to see the probability for T to be 1. If you have multiple values for T, what can we do? Yeah. By generalizing the propensity score, how can you proceed? Why?
I think just marginal treatment effect. And if you don't have a confounders or you satisfy your conditional independence assumption, you just regress the T on your Y, and the coefficient of the T will be the marginal treatment effect.
Right here, you assume there are no, you assume it's ignorability, right?
Yeah, and the T should be like continuous variable.
T is, in our case, T is binary. T is binary, X is discrete or continuous. And Y is generally binary because we are talking about the kind of success or failure. But it doesn't matter. Y could be continuous, X could be continuous. And here we assume T is a binary. And now how can you go from binary variable T to say multi-valued T or even continuous T? Sorry? We'll come back. Yeah. Okay. Yeah. Wonderful. So basically, here you don't really care. Even if T is a T has many values, you don't care because as long as you can. What happened? I think there's some problem.
If you want to update.
Yeah. Okay. So as long as this condition holds true, where is it? Right here. As long as this condition holds true, then this equation will follow. That means I don't care. For instance, I can even use the 3 functions, 3 dimensions for the propensity score. For instance, suppose T has 8 possible values. And I can just say, oh, right here, I can consider that as a concatenation of 3 binary variables. And then for each of them, I can find the function. If I put them together, then I have 3-dimensional propensity score. I can use it the same way, right? So as long as this condition holds true, it's fine. Even if T is continuous, you can do the same thing. For instance, when we do regression, suppose we are doing regression from X to T. Is that right? Yeah, we are doing regression from X to T. Generally speaking, we are trying to make, where's the original graph? Or maybe I can just go back to this slide. Right here, you can see we want to find this guy so that they are conditionally independent. Even if T is continuous, when we do regression, what do we want to achieve? Suppose you regress T on X. What do you want to achieve? Generally speaking, in regression, T is a function of X plus noise. This is the regression model, right? So of course, here we assume noise is additive. This is a very strong assumption, but in general, you can make it more flexible. You can even have this model. T is a function of X and noise, right? And then if noise and X are independent, then we can say T and X are conditionally independent given the function X. This is the property of nonlinear regression. If you assume the noise is additive, Can you see it? So now basically this one can also serve as this kind of propensity score because this one makes T and X conditionally independent. That's the assumption. If that one satisfied, it's safe. And you follow, right? This part is clear, right? Even when you do regression with a continuous target variable, you don't really care as long as the noise is additive. And if they are independent, in regression, you try to find independent residual, right? And then T and X will be conditionally independent given fx. And you can consider this guy as some kind of propensity score in your case. Good? Okay. Yeah, any other question? Could you please louder?
So the first question is that on the example of like sodium intake on blood.
Yes, let me go back to the example. Right here, right?
And why the regression result is different from the true average treatment impact?
Okay, good. This is because although this is simulated data, you have a data set with a finite sample size, right? And you have random error. Right here, when you capture the empirical average, right here, we have random error because you only have a finite number of data points, xi. That's why when you use the empirical the average to replace the mean, there's a difference. That's why.
So it should be.
And of course, right, in addition to that, the estimation of the conditional model can also introduce some random error. That's why.
So a second question is under what circumstance should we use this for instead of regression?
Oh, okay, very good. If you can easily estimate this model, I would say you can just use it. If you can easily estimate this model from data, you can use a regression adjustment. In some cases, it could be very hard. For instance, if you have very high dimensions for X, right? And then this regression problem itself can be very hard. Because you have, if the dimensionality of T of X is very high, then estimation of this model could be pretty difficult. You have a lot of random error.
For example, the positivity assumption isn't satisfied, or it's because there is some lack here.
Yes, possibly because of complex relationships, the nonlinear relationship. We assume positivity assumption holds true. Yeah, if it does not hold true, then basically you don't have a guarantee, right? It may not be consistent. Good. Any other questions? No, maybe we should take a break. Yeah. Thank you. Please come back in 15 minutes, and then you will see different framework. We are going to use the graphical model, the graphical representation to deal with those problems. So let's continue. Oh, I don't know. Actually, you are interested in this part. That's such a surprise. Okay. I try to include this part to make this course more complete. Why? Because we are going to focus more on the structure, right? Regarding how you can really learn the structure. Good. Now, let's go. Yeah, so to go to the slide directly. So you saw ignorability. Now let's try to use the following. You are given structure, the causal structure. And then, first of all, that framework is really beautiful. Second of all, can you test whether this is true? How can you really see, or how can you be sure that this is the case? Any idea? We assume ignorability and strong conditional ignorability, right? Can you test it? Generally speaking, in order to do so, we have to do some kind of structural learning, right? And before that, maybe you want to find a structural way to encode almost the same condition, right? And now let's see how we can make use of graph to solve this problem. And later you can see how we can really verify this condition. This is a backdoor criterion. Actually, Peter Sprotted also came up with some condition like this one at some point. And this name is very good, given by Udall Pro, backdoor criterion. So it's very intuitive, and it got very popular. Right here, so we say a set of variables Z satisfy the backdoor criterion relative to the ordered pair of variables xi, xj, if the two conditions hold true. They are very intuitive. The first condition says that no node in the variable set Z is a descendant of xi. Okay, so we are considering ordered pair xi, xj. So first condition, no node in Z is a descendant of xi. And the second one says that Z blocks all paths into between xi and xj that contain arrow into xi. That's what I mean by backdoor paths. Okay, it's a path between xi and xj, and it's into xi. It has arrow into xi. That's backdoor path. If the two conditions hold true, we can immediately apply this equation to do the backdoor adjustment. And this looks familiar. This is exactly what we did when one conditional ignorability holds true. Different groups, we have the conditional distribution, and then we have the same. This is in that case we use X. So we use the marginal distribution right here for the adjustment. It's exactly the same thing. Now we just use Z as that guy. Now let's just given a graphical model. Suppose we have a graphical representation. Let's see whether this condition holds true or not. And then you have an intuition behind this condition. Suppose Z is a set of variables x3 and x4. Do you think the backdoor criterion holds true relative to xi, xj? Yes or no? We are given x3 and x4. First of all, they are neither of them is a descendant of xi, right? So the first condition holds true. The second condition says that x3 and x4 must block each of those paths between xi and xj with arrow into xi. Do you think that condition holds true? We have this one, we have this one, we have this one, and so on. We have 4 paths, backdoor paths. Do you think all of them are blocked by x3 and x4? Yes, right? Yes, you can, this separation, so we can do so. Okay, good. If that's the case, we can just use Z right here to find the causal effect of xi on xj. And let's consider a very simple case first, as you see from here. Do I have that? Okay, here. X causes t and y. This could be age. T causes y right here. Do you think X satisfies the backdoor criterion relative to t and y? That's the common cause, right? And clearly it holds true because this one blocks. So essentially this one, you can see, this one is somehow related to deconfounding. I just want to find a common cause to block all those backdoor paths. And then I can use those confounders to do adjustment to find the causal effect of t on y or xi on xj, or generally the causal effect of x on y. Okay, so let's look at the second example. If t is x4 and 5, do you think the condition holds true? Okay, to make it very quick. Yes? No? No? Why? Which path is open? It's yes, right? Okay, good. What if Z is the x4? Yes or no? No, because of M, right? Because of M path. Good. Now let's look at another example. Let's make it simpler. So we have xi, xj right here. We have z right here. we have say W and V. Do you think the empty set satisfy the backdoor criterion relative to Xi, Xj? Yes, right, because I have a collider, the collider is not there. Good. Do you think Z, set of variable Z, satisfy the backdoor criterion? No. So that means if you want to use this one for the adjustment, it's wrong, right? If you don't use anything, it's fine. So it's not necessary to say that the more information you use, the better the result will be, right? You can see kind of examples. Furthermore, if you have Z and W together, right here, do you think the backdoor criterion is satisfied? Yes. Okay, good. So it's really kind of, we have to be very careful. Good. This is the backdoor criterion. You can see how we can do adjustment. And this is the front door criterion. It's also very intuitive. Z is here. Here we have a path from X to Y, and Z can only be here. You can also have latent confounders right here. You don't care. As long as this condition holds true, you can do the adjustment. In theory, you can even think of this situation as the case where you can apply the backdoor criterion twice. Okay, I will skip the details, but basically, if you have such a Z variable, although you have latent confounder for X and Y, you can identify the causal effect of X on Y by making use of Z. You can do adjustment this way. Okay. And let me skip an example. Today we don't have enough time. So, and this is a way to relate that to potential outcome framework. It's a summary of the potential outcome framework. Let's go further. Right here, this is the backdoor criterion. Basically, it says that, oh, Y of X is independent from X given Z. Essentially, backdoor criterion corresponds to the ignorability or conditional ignorability condition, right? Given Z, which satisfies the backdoor criterion, then Y of X will be independent from X. Okay, so you can see the connection. And similarly, right here, you can see the condition formulated in the potential outcome framework corresponding to the front door criterion. The first one says that, oh, the outcome, if you have Z and X as input right here, the outcome would be the same as the situation where you have only Z as input. You can ignore X. This means, oh, here you can see all the effect influence from X to Y takes place via Z. That's why I can ignore X when I try to see the potential outcome. Right? This is the first condition. The second one basically is also the independence between the mechanism here, right here, is independent from this mechanism and this mechanism. They can share information. So this one, Y of Z, this part, the property here, and X, they can share information because of U. But if you put them together, they are independent from the mechanism from X to Z, because there are no other way for them to be related. For instance, if you have a link from U to Z, then this condition is violated, right? We don't have the front door criterion, then we cannot use the front door adjustment. Good. This is a formulation in the potential outcome framework, and you can see the correspondence. Which one would you like to use? First of all, graphical one is more intuitive. And second of all, as long as this condition holds true, I can just derive the additive matter step by step. It's completely rigorous if that one holds true. But if you want to go from the graph to the properties you want to make use of in statistics, there's always some assumption, right? Let me give one example. So even if, for instance, right here, even if we have this graphical representation, this one can be 0. And sometimes we can have a cancellation. Even if we have link from X to Y, there could be a cancellation in the causal effect, right? They can be independent. So it's nice, it's intuitive to use the graph to represent independence and conditional impact relations. But sometimes you may have extra independence or conditional impact relations in the data compared to the deseparation patterns in the graph, right? So from that perspective, it's more kind of direct to use the potential outcome framework, because that's exactly what you need in order to derive the final estimate. Let me ask one more thing. Suppose you can do randomized controlled experiments. You want to see the causal influence of X and Y. Do you need to assume anything? Do you need to assume some kind of faithfulness? You want to see whether X caused Y, right? So you do randomized controlled experiments, or you do intervention on X, and you want to see whether there's a change in the distribution Y, right? Do you need to assume anything? Because you try to make use of the observational data to say something about the process. Generally speaking, we still need to assume something like faithfulness, because it is possible that in one situation, there are multiple ways for X to influence Y, but by accident, the causal effect is 0 because of cancellation, right? So if you really want to say that, oh, X does not cause Y, you really need to make some assumptions in order to relate what you can observe to the underlying process. And later, I will formulate a faithfulness assumption and some other assumptions once again, but it's not a surprise. Whenever you want to go from one world to another, you need to make assumptions. Okay, so, and you can see you see the correspondence between them. Now you can see a unification of the graphical criteria. Right here, this is a sufficient condition in terms of the graphical properties. Basically, a sufficient condition for identifying the causal effect of X and Y is the following thing. There exists no bidirected path between X and any of its children. It looks kind of not so straightforward, but let's just look at this condition by making use of some examples. Basically, if this condition holds true, if this one holds true, then we say, yes, the causal effect of X and Y is identifiable. That's why it's identifiability condition. Okay, right here, do you think this condition also holds true? Here, by the way, by the bidirected path, I mean a path consisting of only bidirected arcs. And by bidirected arc, I mean the following thing. You have those two variables, X and Z. They have a variable, and this variable is not observable. You have a latent confounder there. If you don't want to include this guy, then you can have this arc. It's bidirected, right? So if the bidirected, it just means that, oh, here I have a latent confounder. I don't measure it. That's why I don't want to draw. I don't want to give this variable here, but there is some guy causally influencing both X and Z. This is what we mean by bidirect arc or bidirect link. Okay, now let's check the condition. Example A, do you think this condition holds true? Y is a child of X. Is there a bidirected path between X and Y? Yes, right? This is a bidirect arc to denote that they are the latent confounder for X, Y. Clearly, this is violated. Second one, you have Z here. Do you think you can do you think the condition holds true? It's the same thing, right? It's violated. Again, it's violated. Now let's look at more examples. Remember this example right here. Later, you can see under some assumptions, you can still identify the causal effect of X and Y. Although in the general case, in the non-parametric case, we cannot, because this condition is not satisfied. In this case, do you think the condition holds true? X causes Y. Yes, right? Clearly, there are no bidirect paths between X and Y. Y is the only child here. Here, do you think it holds true? Right? Okay, good. In all those cases, even if the graph is very complex here, the condition holds true, then we can identify the causal effect of X and Y in all those cases. Here you can see that's also the case. Basically, this is a frontal criterion, but there are no bidirected paths between X and any of its children. The only child is Z. There are no bidirected paths. Although there's a bidirected path between X and Y is not a child of X. Okay. Okay. So graphical criteria are more intuitive. So here you can see a lot of examples where the condition is not satisfied. You already saw some of them, right? Okay, in those cases, we cannot just say, oh, the causal effect of X on Y is identifiable. Now let's look at one more example. Remember this example. So now in the non-parametric case, we cannot identify the causal effect of X and Y. What if the whole world is linear? So basically, we assume each causal influence follows the linear model. And then in that case, you want to identify the coefficient of the model from XY, of the linear model from XY. Do you think it's identifiable? And this is actually very well known. Z here is known as a instrumental variable, right? Cool. So although you have latent command here, say you influence both of them, you don't really care as long as you have such a variable Z. Z directly influences only X. Then we have the following property. First of all, you can find the product of X, alpha and beta. If the variables are standardized with a unit variance, then alpha times beta is nothing but the covariance between Z and Y, right? And furthermore, you can estimate beta, right? Because it's just a correlation between them, or you can do regression, you can find the beta. And then alpha is nothing but the ratio. So that means if you have parametric assumptions, you can go beyond the graphical criteria because the such space is so much smaller, right? Okay, so this is instrumental variable scenario. In the linear case, we know it's identifiable, but in the general nonlinear case, it's not identifiable. With some assumptions on the nonlinear functions, it might be identifiable. In machine learning, some people already developed some methods to identify causal effect of X and Y, even if the relations are nonlinear. You have to make assumptions. Okay. Now, how much time do we have? Okay.
Yeah, about 80 minutes.
We can finish this part, and we can make the discussion shorter. Now let's look at the following problem. You look at the picture before. Now we want to see how to do counterfactual reasoning right here. You are given something, and then you want to say something about variable of interest, say x3, given the intervention or x2. In this case, remember the question. We observe George does not have yellow fingers and coughs. We observe that. And then you want to see, would George cough had he had yellow fingers? In this case, first of all, if you ignore the evidence, what would you say? If you do intervention so that George had yellow fingers, the chance for George to be to cough would be relatively high, right? Because there's a high dependence in the whole population. In the whole population, if you just do intervention here, then the chance for the person to cough would be relatively high. Yeah, but now you have more information. You can see for George, he does not have yellow fingers and he coughs. You know that. Then after intervention, so that George has yellow fingers, do you think the chance for George to cough is very high? Clearly, it's even higher, right? So in this case, you can see by paying attention to a particular subject, you can make the answer much more informative. Okay, you saw this picture before. right here, this is the conditional mean of y given x. In machine learning, you just want to predict y from x. You use the value of x as input. Good. Now, as you saw from the answer, you can go beyond that. You can make the answer more specific by discovering hidden information in this particular subject. So suppose x called y, no. Suppose we are given the causal model. Later you can see it's not necessary to assume that causal model is given. We have data points here. And then for this is me, as I just mentioned, I have this attendance, I have this grade. Now you do intervention. So this is my new attendance after intervention. You want to see my value of y. That's it. And I hope the intuition is very clear. Right here, you know, if you observe this data point, you have some understanding about me, right? I may not pay attention. I'm not so kind of smart in some way and so on. You have the understanding. And then since you know that this intervention on attendance will not change my particular inherent feature, you can still make use of that property. You know, oh, after intervention, I'm still kind of not very smart, or I don't pay very much attention, right? So after that, you know, oh, my value of y should be somewhere here. This is because relative to the whole population, this is basically my location relative to the whole population, right? You can see it's the same, right? So later you can see how we can formalize this procedure. Good, this is the definition of the problem. You observe something about me, and then you are to see what the y value would be if x had been different. Okay. Okay, good. So this is here you can see a formalization of the standard counterfactual reasoning question. We are talking about a particular situation or particular subject or particular unit. That's it. We have this value of the u is the unit. Here is a random variable, and the small u is a particular value, right? We are talking about a specific subject, and then you want to see what value y would be had x been a different value x prime in the situation u. So basically, you want to say something about this one. This is a potential outcome, right? So for this particular unit, U. And then for this unit, clearly, for us, we know, oh, we are talking about you, we are talking about me, right? But if you want to do statistical inference, you have to give evidence. This is the evidence. You observe value of x, value of y, or something else. You condition on such a thing. And then you just want to go further. Previously, when I talk about the identification of causal effects, we just consider random variables. U is a random variable because we don't fix U every time we try to take the expectation, right? Now, we are trying to make use of a specific property for this unit. Let's see how we can go further. So basically, this is the standard procedure with 3 steps formulated by Pearl. The first step is called abduction. You are giving evidence, and then I want to find a way to discover the hidden information from the evidence. In this case, suppose you are given graphical causal representation right here. You observe values of say x, y, z, or some of them, and then you try to say something about the unobserved variables u. By u, I mean unobserved variable or noise. You can always find a posterior distribution. In some cases, you may have very strong evidence, so that you can have a lot of information about about the hidden variable, right? You may even have a unique value for u in some cases. But generally speaking, you just want to discover the information of the unmeasured variables u from the evidence, represented by the conditional distribution of u given evidence. That's the standard thing, right? This is abduction, and then you do action, you do intervention. You just change the value of x to x prime. Now, you understand me because you make use of evidence to say something about my hidden features, and then you also did intervention on me. You just want to find the value of y corresponding to this new value of x and the evidence or the information of the hidden features. Now let's look at this problem again and see how we can answer the question. Oh, this slide, where's the that's okay? One slide is missing. Let me just draw it here. I will just send you updated slide. I think I still have it here. Maybe I just hit the pro slide. Okay, to save time, let's just go. Let me just draw it on my iPad. Let's see how we can answer this question. So right here, first of all, we are giving the values of x, y. And then we can infer the information of the hidden variable, which is u here, you unobserved, right? A noise. From this x, y value, we can derive this. What's u? U would be, from this equation, we can see u would be e to the y variable minus x minus 3, right? So this is how you can go from x, y to the hidden variable u. You just try to make use of x, y to say something about the u hidden variable, right? So this is it's just followed from the causal model. And then for the given x, y value here, we can just write down, oh, this u, particular u value for this person is e to the y minus x minus 3. Right? Now you understand me, because you know the noise value right here. And then we just want to see the value of y given this intervention, given the evidence. What's this? I still use the causal model because the generating process will still follow the causal model. The causal model is right here, is here. But now I'm going to use two new things. One is the new value of u, as you can see from here. The other is the new value of x, because you did the intervention. Okay, so now basically you can just write down. This one would be log x prime plus e y minus x minus 3 plus 3. Is that right? Okay, and then this is nothing but log is x prime plus e y minus x. So now you can see this is the function in terms of the evidence x, y values and the new value of x, right? And this is the answer to the question. Of course, in this case, you can see it's very simple because we can directly find the value of u. In the general case, you just use the posterior distribution. That's the best way to capture the information you have. And then you can just go further. And finally, you have the probability distribution for this variable, for this potential outcome variable, right? Good. Oh, y, okay, in this case, capital Y is a random variable. So let me give a relatively real example. X is the attendance, and Y is the final grade. So attendance influences the final grade. And then small y is a particular value observed. So right here, this is basically the value for me. You observe value of x, small x, and value y, small y. for me. Good. And now you try to see the value of y. If x had been different value x prime for me. That's why you want to make use of small x, small y to characterize this particular subject and the new value of x because you are doing intervention.
So the x will be new, but the y is the old y.
Oh, no. So x is new right here. You are right. Here, x is new, and this is the new y value. You are estimating this way. You want to see what value y would take if x had been different, had been x prime for me, with x, small y as the values for x and y. So, yeah, you are, what do you mean by it? You are using the same evidence?
X prime, and another X prime, I will use the same.
Wonderful. So yes, now suppose, now we are talking about this particular person. Suppose we are talking about another person with value say x star, y star, right? Then this is the different person. I have to use x star, y star to replace xy right here. Because for this new value, even if suppose x is different but y is the same, right? Still is a different person. You have to infer the information of u from this new value of xy, corresponding to a new subject.
So you don't borrow any strength, like, like U is common to all the people, so you don't borrow any strength because you have more people, rather you have a lot of data. So if there's a common pattern, common unknown, so do you borrow strength there, or you do individualization every time?
Oh, I would say for counterfactual, you do individualization every time. However, clearly you can see in this example, we have it's an artificial example. So we have a value for y for this potential outcome for this guy, this one, right? For this one. In reality, you may have a distribution, or you may just have the expectation. For instance, what if we have another guy, say, W? Let me give an example. Suppose this is the case. This is the causal model. W causes X and Y. Oh, it's so messy. Let me just clean everything. So suppose this is the true causal model. Now, in addition to this, you also have W and so on to be determined from the observed evidence. In that case, you don't have a unique value. Instead, you just have some kind of informative distribution given by probability distribution of U right here and W, given the evidence. Clearly, you cannot determine the values uniquely. You can only have a distribution, right? And later, you just make use of this distribution and the new value of X to give the distribution for this outcome, potential outcome, also for this counterfactual outcome. That's it. So that's why in the general case, you may not have a single value, but you can always find a conditional, find the expectation, for instance.
So in practice, can we just do the percentile regression? If I say percentile regression,
Did you get the question? In practice, can we just use some kind of quantile regression to solve the problem? Wonderful. Yes, we are doing that. Yes. So why? Because that's the next, if you go to next slide, you'll see why. This is one of the points I want to discuss. I'll come back to this point later. It's genius. Okay. Any other questions here?
The inference, the counterfactual inference at the base and the first, it looks like they have a similar logic.
Oh, so basic question is whether there is a difference between counterfactual inference and the Bayesian inference, right? I would say that completely different things. they are at different levels because Bayesian inference is the fundamental way for you to do inference, right? As long as you have a model, you have prior, you have a conditional, and then you can always go further. You can find the joint, you can find the posterior, right? So that's just a general framework for you to do statistical inference. And the counterfactual inference is the one particular thing you want to do in the causal world by making use of the graphical representation, causal model, and the statistical Bayesian inference. That's why here you can see we have the conditional distribution or posterior distribution of the unknowns given the evidence. We can always make use of Bayesian inference, but the problem is at a different level. Is the answer to your question? Okay, so
Sorry, in this example, are we trying to estimate the individual treatment? Are they sort of related or the same thing?
oh, wonderful. So the question is, in this example, actually, is this the same as estimation of treatment effect, right? Given this particular subject, individual treatment effect. How would you like to respond to this point? If you find a difference right here, suppose this is T, to make it it's T1, T0, right? Oh, so ugly. Given the same thing. Basically, you are doing something like individualized treatment effect estimation. The problem is here, you just condition on the evidence. It might not be informative enough. If you just use evidence to estimate the treatment effect, then it's the same thing. Because this is nothing but a potential outcome given the evidence, right? It's just the difference between the two potential outcomes with different value of T in treatment studies, given the evidence.
So X here is not a treatment.
Oh, X, no, this is the general framework. So X could be anything. Yeah. And even in the treatment studies, basically we use treatment because we have kind of historical reasons, right? Usually we are concerned with the treatment effect, but T can be anything, right? It can be vaccination, and it can be, say, temperature, and so on. Okay. Then let's just move forward. First of all, to summarize, the counterfactual reasoning is really a kind of standard way for you to discover the hidden information of the subject and make use of it. That's really the, if you are confident that you understand me, this is what you can do. You have to discover the hidden things that others may not see. Then you can really have something, have very good understanding, and you can really predict the potential outcome for this guy under different situations, right? Second, do we really need a structural equation model or structural causal model for counterfactual reasoning? Previously, we had this model right here. We made use of this model to find the value of U or find the posterior distribution of U, given the evidence, and then we proceed to find the value or the distribution of this guy. Is this necessary to have this model? Actually, it's not necessary. If you assume, for example, if you assume the noise term here is recoverable, so suppose this function is invertible, given, so for any value of x, this U can be written as a function y, suppose that's the case, then now you don't really want to have this model. It's not necessary for you to have this model because, as you just mentioned, my hidden property in this case, basically, given different values of x, my value will always be on this curve. Why? Because my value of U does not change. And then my relative location relative to the conditional distribution y equals x is the same. So that's why it is possible to use non-parametric or nonlinear quantile regression to solve the problem. Okay, it might be a little bit kind of advanced because you have to basically rely on the conditional distribution, and then you can see that as long as you fix the value of U, the quantile, basically the relative location for me will always be the same. Okay, because this relative location just describes how smart, say, I am compared to the whole population. That part is fixed, even if you do intervention. Good. Okay. Our last question. Do you really agree that this is the optimal way to go with, in the general case, if you want to do counterfactual inference? Is there any other issue you want to raise in order to really make counterfactual reasoning very practical and very natural? For instance, let me give one example. Here, we have X called Y. Suppose here, of course, X may have other causes, say W. Here, you want to do intervention on X. You want to set X to X prime, right? In this framework, you don't care about anything else. You just do it. Do you think it's possible that this value of X prime relative to the observed value of W is very strange? Then this counterfactual data point would be very strange. It may not make sense. Consider some kind of inherent features for people in of different genders, right? You can really say, oh, if you want to change one thing, yes, if the relationship right here is stable, you may want to preserve the mechanism or the stable law right there. A violation of this law can really cause a lot of trouble, right? So this is just one problem. I mean, when you do counterfactual reasoning, maybe you also want to consider other factors. This is just a basic framework, right? So in your scenario, maybe you can derive some other kind of variants of counterfactual reasoning in order to really solve the problem better. Last thing, in some other fields that define counterfactual reasoning in different ways. For instance, some people say, oh, in order to do counterfactual reasoning, I just try to find the data point in the alternative world in which X has this new value. You consider alternative world where X has a different value, right? So you can see that's a very simple way to put counterfactual reasoning. At the same time, it may not be really rigorous enough because inherently, or basically, counterfactual reasoning is a causal problem. Without using the causal notion, you cannot recover the underlying hidden information for the particular subject.
So,
okay.
Basically, we have to be able to simulate an individual, right, to get it. If we can simulate, then we can, have the results for both treated or untreated, and find the difference. That can also be used that way, right?
Yeah, totally right. If we can do that, then potential outcomes are not potential anymore.
Right, right.
If you really have twins, right, ideal twins, then you can really say that.
Right.
Yeah, totally right. But generally speaking, the potential is counterfactual. Yeah. So I'll stop here. But basically, there's a long story regarding that. I completely agree. That's a very good idea. But generally speaking, it's counterfactual. Any other questions? Then let's do a summary right here. First of all, for counterfactual, for identification of causal effects, what do we take as input? Maybe I can find a volunteer to give a very quick recap to answer the questions. Anyone would like to answer my questions? Anyone? You want to give it a try? Okay, so let me answer questions. So in identification of causal effects, what do we take as input? There are two things. One is a qualitative structure, causal structure. The other is observational data for the measured variables, right? Given that, we can try to see whether the causal effect of X and Y is identifiable. If it is, then we can just follow some rules to do adjustment to produce the causal effect. Second, in potential outcome framework, basically you can see Y is potential, and you can see how you can really deal with this variable, and you can see how to understand this kind of variable, right? Potential outcome thing is a way to describe the mechanism to generate the outcome Y, given fixed values of the treatment. And you can see how we can solve the problem in the potential outcome framework. And you also saw some graphical criteria on the causal structure, under which we know the causal effect of X and Y is identifiable. Okay, it's more intuitive. At the same time, you can see, generally speaking, in order to go from graph to the property like this one, we need to make some assumptions, although in many cases we have those assumptions implicitly. And you saw the definition of propensity score, and you can see why propensity score might be a very appealing concept, although in practice there might be some other issues. And finally, you can see the difference between counterfactual reasoning and prediction in machine learning. And furthermore, you may want to formulate a number of new problems in the space of counterfactual reasoning, and then you can go further to make it better. Okay, thank you very much.